has worked in school, in high school.
I see. Oh, okay. So I received one email from the department saying there's no holiday today. I'm not sure if you guys received the same email or not.
No, I went on the website, and the first thing they tell you is that there's still classes on Monday, so.
But we get Cesar Chavez's day off.
What's that?
Cesar Chavez, which is weird, because.
Oh, yeah, I remember that, yeah.
Yeah.
Like the first Hispanic mayor?
No, he led.
The migrant farm workers help them get better the unions.
Yeah,
For the
labor.
farm unions.
Okay.
Yeah.
For farmers, yeah, but we don't get the prejudice.
Because we're seasonal, we're Hispanic. Well, majority.
It's on Monday or Wednesday?
What's that?
The holiday was just
I don't know.
Cesar Chavez. It's always on a Friday.
Friday.
Seems like.
It's not going to affect our.
No.
Yeah.
Holidays never. I never get
Day
class.
off. We're very
So this deal about president is just for Trump, this is all the time. We're
Yeah.
not taking a day off for every president. No, it's not just for Trump.
No, they never celebrate it here.
Okay.
No, they used to. 4 years ago. My sister.
Okay, so let's begin our lecture today. Last week we were talking about gradient. It's the original derivatives, the rational vectors, the maximum direction, the direction where you can achieve the maximum rate of change, those kind of things. At the end of the lecture, I went a little quick, so I want to review some of the key points from last week. So basically, we have z is equal to f of x1. So we're still looking at a function with two independent variables and gradient. And also, to remind you constantly, gradient vector is defined as a vector with x component as the partial derivative with respect to x, and y component as the partial derivative with respect to y. In its very symmetric form, and also we have this notation: gradient f is equal to fx and ffy. And I want to stress again, this is a vector. Okay. And also we have this directional derivative. Where it is denoted as duf. Okay, so the formula says this is equal to gradient ff dot with the directional vector, where here directional vector is really a unit vector. It's given by u1, u2. Okay, so u is a directional vector sitting on the xy plane with two components. Well, so we can do this dot product between one, two vector, and the other one, two vector, right? So this is just a u1 times fx plus u2 times fy. So this basically is a number. So there are three key objects we introduced in last week: gradient vector, directional unit vector, and directional derivative about the rate of change when you specify one direction. Okay? And also we have the following formula. We want to achieve the maximum rate of change in the direction of u maximum. This is equal to, what's the formula for u max? Gradient normalized, right? And also we have the u minimum is equal to minus gradient normalized. And remembering these formulas is pretty helpful. You can also remind you this gradient is a vector, right? Then normalize it, you're getting a unit vector. So three objects, two are vectors, the other one is a scalar, okay? And we can also compute the maximum rate of change achieved at the direction of u max is equal to, what is this guy? The maximum rate of change of a function is achieved in this direction, and the rate of change is equal to
length of gradient?
You don't have to remember all the formulas, but you have to remember some of them. Right? For instance, if you know the directional derivative is equal to gradient dot product with this direction, and I know U max is equal to gradient normalized, then this guy is equal to dot with U max, and it is equal to gradient of f dot with gradient normalized, right? So U gradient dot with gradient, you're getting a length squared, right? So this is going to give you the length of the gradient. If you still remember what we did for last lecture, which is the equivalent argument, we write in a geometric form. This guy is equal to length of gradient times length of unit vector, which is just equal to 1 and cosine theta. Remember? So that's where we actually verify when theta is equal to 0, that's where you achieve the maximum rate of change, which is exactly the length of the gradient. Theta equals 0, then U has to be in the same direction, which has to be also normalized. That's where we derive our formula, right? Remember? Okay. And also we see when theta is equal to pi, we're getting minus length of the gradient. That's the minimum rate of change. F is equal to minimum minus length of the gradient. Okay. So these are the key formulas we achieved from last lecture. So fundamentally, you have to always remember this is a vector, this guy is a vector, and this guy is a scalar. Okay? All the formulas are actually consistent with their nature. Right? So when you are doing the dot product, we can do things. Both of these two are vectors, right? That's why you can do dot product. And then I'm computing the directional derivative. I'm getting a length of the vector, which is exactly a scalar. All right, so all the formulas should be consistent with the nature of the objects. This is extremely simple questions, as long as you remember how to compute them, right? What I saw very frequently in the previous semesters I taught these things, people forget what they are, and they just randomly remember some formulas, one from the probably 6, and then they just start any number you can find in the problem, which is pretty pathetic in the end. If you remember all the nature, the formulas are pretty subjective. Okay, so remember the nature of the 3 objects first, and then the following formulas are pretty natural, right? Mm-hmm. These ones are pretty natural, as long as you know what they are. Questions? And also, I mentioned in the very end, we can define the same thing for functions involving 3 independent variables as well. Right? So if you have 3 independent variables, we can still define a gradient vector. The gradient vector now is going to be a vector in R3. It is still denoted as gradient of f equals fx, fy, and fz. Okay, so it is still in its symmetric form. So the x component is the partial derivative with respect to x and so on. So it is a 3 vector. And we can also define the directional derivative. Still a scalar. If you specify a direction in R3, this is equal to gradient of f dot product with the directional derivative, where this directional derivative is going to be U is going to be equal to U1, U2, U3. Right? So the directional derivative is the inner product between the gradient and the directional vector. So if you expand it, it's going to be U1 fx plus U2 fy plus U3 f3. Okay? So you can still define the 3 objects here. 2 are vectors, 1 is a number. And then you can still ask yourself in which direction I can achieve the maximum rate of change. The formulas are exactly the same. All right? I can still get the maximum, the direction where I can achieve the maximum rate of change. This is going to be a normalized gradient, but because gradient is a 3 vector, all right? Mm-hmm. In the case where you have 3 independent variables, so U max is going to be a 3 vector. U mean it's also a 3 vector. Both of these two cases are still the same. Okay? The only difference is instead of you're doing a calculus for 2 vectors, you're doing a calculus for 3 vectors, and that's all. Okay? So I'm going to give you one example to practice, so we can immediately see how we can compute things in 3-dimensional space. So if I have a function equals 3x squared plus 4y squared minus 4z squared plus 9 is equal to 0, and I add e minus 1, 1, and 2, I want to compute the gradient vector, and also the gradient vector evaluated at minus 1, 1, and 2. Okay? I have some students in mind I want to mention. Is George here? George. Okay, so work with me, please. So I want to compute the gradient vector according to this symmetric definition. So basically, I'm just asking you to take the partial derivatives, right? Yeah. So partial derivative with respect to x, we got 6x. And partial derivative with respect to y, 8y.
Negative 8c.
Minus 8c. Very good. So remember, gradient vector. And also, when I evaluate at a given point, I'm supposed to have a vector as well. So let's evaluate what happens when x is equal to minus 1, y equals 1, and z equals 2. Negative 6.
8.
8.
And negative 16.
Minus 16. Okay? So this is a gradient vector, right? And now I want to ask, what is the equation of the plane? Plane that is orthogonal to this gradient vector and passes through this point, minus 1, 1, and 2. Okay, so I want to find an equation which is orthogonal to this vector and passes through minus 1, 1, and 2. So this is testing your equation of a plane, where you know essentially the normal vector and a point. Remember that? So what is the equation for a plane that is orthogonal to a normal vector? So let's see. Normal vector u1, u2, and u3. If it's normal to this vector, it's going to be u1 x plus u2y plus u3z is equal to a number. All right? So this is the general equation for a plane that is orthogonal to a vector in R3. And in order to figure out what this number d is, you need to plug in the point. Right? You need to plug in the point, immediately you'll be able to figure out what the d is. All right? Now with me? This is not like 20 years ago, right? This is only 2 weeks ago. So if I want to find the equation of the plane that is parallel to this vector, it's definitely going to have the format of minus 6x plus 8y minus 16z is equal to a number d. Right? And also, I need it to pass through minus 1, 1, and 2. So the only thing which is left is to plug in numbers. Right? So I plug in numbers, I'm getting a minus 1 minus 6, 6 plus 8 minus 32 is equal to d, so d is equal to 16. Not really 16. 18. D is equal to 18, so the equation should be minus 6x plus 8y minus 16z is equal to 18. If you want, this can be simplified to minus 3x plus 4y minus 8z is equal to 9. And that's pretty much it is. Okay? So this is the equation.
Should it be negative 18?
Oh, I'm sorry, this is supposed to be negative 18. Yeah, sorry. So this is supposed to be negative 18. So we can actually actually move this to the other side, it becomes a plus 9. If you want. Okay, so this is the equation of the plane. Again, why is it a plane? Remember the trick I taught you in the very beginning. All linear. All right? Obviously, all linear has to be a plane. Okay? If you have a vector linear format, it's going to give you a line. But if you have an equation with 3 variables governed by one equation, 2 have to be free, 1 is determined by the other 2, and this is going to be a plane. Right? Plane is an object with 2 degrees of freedom. You have 3 variables governed by one equation. That will give you 2 degrees of freedom. And everything is linear, so this has to be a plane. Questions? Okay. So I can also ask you, in this point, at this point, what is the directional vector where I can achieve maximum rate of change? At this point, where I can achieve the minimal rate of change. Right? So basically, I can also easily compute U max to be, what is it? What is my U max here? According to the formula over there.
-8.
It's going to be gradient
And
then normalized, all right? So I need to do a computation of -6, 8, and 16, then divide by its length. So it's going to be 36 plus 64 plus 256. But there are easy ways to simplify this factor. You can immediately eliminate common factors from these numbers. Right? So this guy can be easily computed. So U mean is going to be minus gradient of f divided by length of the gradient. You can also compute what the rate of the change exactly is at U minimum and U max. Okay? So this can all be done regardless of how many independent variables you have. You can have 2 independent variables, you can have 3 independent variables, you can even have 4 or 5, whatever number of independent variables. The gradient vector is going to be always defined in a symmetric form. The directional derivative is always a number, directional vector is always unit vector, and this U max and U min are always defined in this format. Okay? Brian has a question.